The ongoing search for exoplanets is a valuable scientific venture that could answer numerous physical questions regarding the formation and evolution of star systems, and answers to questions in the field of astrobiology, the study of extraterrestrial life. This beautiful graphic is an artist's representation of extraterrestrial planets from the European Space Agency. In this presentation, I'm going to introduce a number of ways of detecting exoplanets, and then attempt to explain to you why the star system HR 8799 is super cool and why you should care about this graphic. Historically, exoplanets have been discovered using two key methods: the, quote, wobble method, or the radial velocity method, shown in green on this graph, and the transit method, a newer and more effective method, which is shown in purple on this graph. As shown in this graphic from NASA, the radial velocity method, also known as Doppler spectroscopy, works by tracking the gravitational pull of a planet on its star, and how this impacts the radial velocity of the star. This is what causes the star to wobble side to side from the center of mass of the star-planet system. This beautiful graphic gives some sense of the center of mass of a star-planet system, showing that it's not at the Sun, but rather a small distance away. We measured the changes in radial velocity by using Doppler spectroscopy, or tracking the slight shift in the light from a star due to the Doppler effect. The radial velocity method has two key shortcomings. Namely, it only works to detect large super-Jupiter planets that can pull on their sun enough to make it wobble, and it requires us to view the system from the correct angle to be able to pick up on that wobbling star. This brings us to the second method, or second key method represented on this graph, which is the primary transit method shown in purple. This method is conceptually simpler. It relies on this very minute dimming of a star regularly as an exoplanet orbits across that star, similar to this transit of Venus across our Sun. The Kepler Space Telescope was essential to this huge peak in detections from the transit method over the past few years. And if you're wondering, as I did, whether the Kepler telescope is still up there, please don't Google "did Kepler die?" because that will get you the death location of Johannes Kepler and not the information that you look for. But yes, Kepler ran out of fuel back in 2018, and this is the last image that Kepler provided NASA with. But now, back into the meat of my discussion. A lot of the focus on the search for exoplanets is on finding Earth-like planets that could support Earth-like life. However, I decided to take my presentation in a different direction, and instead I'm focusing on everyone's favorite star, HR 8799. While it may not have a catchy name, this star system is actually especially cool. As illustrated in this short video, created by compiling data over approximately 5 years, this star system is one of the very first that we were able to detect the planets orbiting an extrasolar star with direct imaging. So where is HR 8799? It is within the constellation Pegasus, which is visible from my area at around 3 a.m. each night. Pegasus is known for looking like a partially beheaded upside-down horse, or, if you prefer, like a great square. While 8799 is typically not visible to the naked eye, this graphic does show where you could find it within the Great Square of Pegasus. HR 8799 is an A5 star with a notable lack of metals in its outer atmosphere, giving it the class designation Lambda Boo. It is located 129 light years away from Earth, and its age is estimated to be between 30 and 1,000 million years, based on its position in the HR diagram. This graphic gives more details on the planetary system surrounding HR 8799. There are 4 detected planets, all of which are approximately the size of Jupiter, and orbit very far away from their star. This graphic illustrates the size of the planet's orbits. You can see, for example, that planet E, the closest to the star, is still farther out than Saturn's orbit. This is planet B of the system, the farthest from the star, or rather an artist's interpretation. Observations using near-infrared spectroscopy have taught us significant information about the planet's atmosphere, indicating that it's hydrogen-rich and also contains evidence of water, carbon monoxide, ammonia, and carbon dioxide. This is an artist's interpretation of the closest planet to the star, E. This planet has an orbital period of 50 Earth years. Similarly to the other 3 planets in this system, E is a very hot and massive super-Jupiter type planet, and relatively young. In 2008, a group of scientists published this paper, which describes the first, or one of the first, detections of exoplanets using direct imaging. This method is most useful for finding Jupiter-like planets, because these planets are far enough away from their stars and bright enough to be directly imaged. So this brings me to what inspired this project in the first place, the gravity instrument used by the European Southern Observatory. The gravity instrument is used to combine light from the ESO's Very Large Telescope array, which creates something equivalent to a single 130-meter diameter telescope. This is an image of the gravity machine, which I cannot begin to understand. But I'd like to leave you with this very beautiful image of the Very Large Telescope beneath the Milky Way.